Let's continue exploring the relationship between localizability and normalizability by coming up with a wave function that describes a localized particle. So let's say that the wave function is such that the particle is between 0 and 1, so the only non-zero values that it should have are in this, in the range 0 and 1, and we'll give it a specific function. So let's say it's some coefficient, a, it could be a complex number, a times 1 minus x in that range, and 0 otherwise, everywhere else. Okay, it's a discontinuous function, but for simplicity, it does what we want to do. So we want to explore the relationship between localizability and normalizability. In the previous example, we saw that when this wasn't obtained, neither was this. Okay, so mathematically, we get that this is not possible if this isn't possible. But now we have the particle is localizable, so this should be possible. So we want to get a sense of that. Let's first draw this function. So at t equals 0, this is x. At x equals 0, we get that psi of x and 0 is a. Well, if a is real, so let's just make a real. So a is greater than 0 and real. And at x equals 1, we get 0. And so the function looks like this. Okay, so otherwise it's 0. So it's discontinuous here. It jumps at x equals 0, it jumps to 0. It goes from 0 to a. And then here it goes to 0 at x equals 1. So clearly the particle is localized. It can only live in this region, and the probability of being closer to 0 is greater, of course, than it is at t equals 0 of being found closer to x equals 1. But the point is, we want to show that now this is a reasonable thing to do, that we can get a value for a for that, and it's everywhere 0 except from 0 to 1, where the function is 1 minus x squared, psi of x modulo squared. Maybe we should just take a step back and write integral psi modulo squared in dx from minus to plus infinity. That's what we're after. And so what do we get? Well, we have a squared times the integral. Let's write this out. 1 minus x squared is the same as, let's see, we get 1 minus 2x plus x squared, which we then integrate, and we have an a squared. If a is complex, then we would just get a modulo squared here, times, oops, I'm going to do the integral. So we'll get integral of dx is just x, integral of 2x is just x squared, and integral of x squared is x cubed over 3. And this has to be evaluated between 0 and 1. So we get a squared times x being 1 minus 0. And so that just gives us 1 minus 1 squared. That's just 1 plus 1 cubed over 3. That looks like that. The zeros here and here also don't give us anything. And so we get that a squared, or a modulo squared, if a were complex, divided by 3, this needs to be equal to 1, and so we can get a condition on a, which is the square root of 3. And if a were complex, it would be the modulus of a is equal to the square root of 3. So if a complex. So notice that these two things go hand in hand.